Right. So yes, last class we're looking at the proofs using the column proof method, where you have your justifications and your conclusions. So we're going to do a few examples of that. And in
Sir,
one
before
particular,
you start, good
who's that now?
afternoon.
Ah, Shanice.
Yes, sir. You don't answer emails, sir. You don't respond to emails.
I do.
You not seen an
I think
email from me, sir?
no, I haven't checked it yet. I haven't checked it today.
Not today, from Monday, because I was trying. I was trying to access the system, but appear problems don't me get through now.
You got, I mean, you registered now?
Yeah, man, I registered from Monday night. I had some issues with the system itself. I wasn't
Oh,
able to do I don't know what happened, but it eventually started out. It looked like the system itself had issues. So by
your
the
man
time
was
the
giving some
class
trouble.
gonna okay. Another thing, sir,
Mm-hmm.
the class that you had, I think it was no, I don't think it was never Monday or whenever audio on, let me see. Like
For
only
the
the audio
geometry,
record.
for this course or the or different course.
This one, I think it was is which one? One of them are audio, like me can't see nothing, I just talking.
Yeah, hold on. I'm in it right now. Let me go see recording transcript.
If it's not this one, it's linear algebra, one of them. Remember which one me that look on. I'm supposed to can see it from here, so I'm telling you. And it's actually audio only. So I say, all right, let me use one different browser to see. And
Is those two courses you're doing with me, linear algebra and this one?
yeah, so
No.
college
All right, let's
geometry,
go.
it says your last class, which was the 19th, it's
Mm-hmm.
audio only. The
College geometry.
recording is audio only.
19th. Oh, look at that now.
Yeah. Yes, sir. The
Download.
19th. A literal audio, and it says audio only. Now I'm gonna click on it. I'm just the audio.
No, okay. All right.
So
So I see here what has more than that. So I'll send the link to you after class.
okay,
Remind me next
please.
class. I'll send the link. All right. All right. Where's the link? now? Back to class. Here we go. Okay, good. So thank you for letting me know. I'll send it to you. Just remind
Yes.
me.
Yes, sir. Will do.
All right.
Sir, how much people at the course here? Two.
Well, you make four now from what I'm seeing.
Wow.
It's I keep forgetting who the girl is. Oh, I think Renee is Harriet is her name. It's
Okay.
you, Renee, Harriet, Harold, and Akeen.
Okay.
You're supposed to know Akeen.
No.
You know Akeen? Okay.
Mm-mm.
As he
But
and you do the same nothing, like both of you disappear and then come back.
oh Lord.
Yeah.
All right, sir. Thanks.
All right. Okay. So proof. Let me give you some simple examples and increase difficulty as we go along. So here's the first one. So each of these questions are going to get some theorems or definitions or axioms. You'll be told what they are, and you're going to use them to prove some hypothesis that we'll come up with. So here's the first one. You're given this. You're given a definition. The definition is A is said to be A is said to be B if and only if P implies Q. All right, that's the definition. Theorem. You're given two theorems. Theorem 1 says P implies R, and theorem 2 says what? Oh, R implies Q. Pretty straightforward. And you're asked to prove this. Prove if P, then A is B. All right, so I want to prove that if P, then A is B. So we have those four things, well, three things. I want to prove that A is B. Sorry, if P is B. All right, so to prove this, we do our normal setup. We have our conclusions, we have our justification for that conclusion. So conclusions first. Justification for why we come to the conclusion over here. Each conclusion needs to be justified. So make sure you can figure out why you put the conclusion. All right, number one. I'm just like put some lines here. Line. Renee, welcome. We're just talking about you. Nothing bad, nothing bad. Just wanted to remember your name because I can't remember who the girl was that was in the class.
Okay, sir, I'm here.
All right. Sorry. So, conclusion. First thing that we need to remember whenever you're given something to prove, the first part is what you're assuming to be true. You're given this thing, you're assuming that it's true, you're working with it. So most proofs, a matter of fact, almost all of them you're going to encounter in this course start from what you're given. You're given P. We don't know what P is, we don't care what it is, we just know that it is said to be true. And justification for the P is that it is given to you. What can we get from P? If you look at up here, theorem 1, we're told that P will lead to R. If P takes place, R will take place. Theorem 1 says from P, we will get R. So P leads to R. How do we know that? Theorem 1 said that. Let me show you how easy it is. What do you think comes next? Based on what we have. We have these three things. What can we get from R? My goodness. Nobody understand? We want to get to Q. Sorry, go ahead. I hear something, Harold?
No, sir. I'm trying to figure.
Okay. So we start with P and we now have R because P led to R. We want to prove that if A is said to be B, sorry, beg your pardon. A is said to be B if P implies Q. So we want to get to A is B. So in order to get to A is B, P has to imply Q. But even if you didn't know that, you can look at what we have. P goes to R in theorem 1. What does R go to? Or what does R imply?
R goes to Q
Right, Q. How do you know that?
in theorem 2.
There you go. Very simple. So R goes to Q. It told us that in theorem 2. And if you look at this part now, remember this part. Here's the trick part now. We want to prove that if P, then A is B. If P is occurring, then A is B. If P is true, if P has occurred, then A is B. That's what we want to prove. We have shown that P will go to R. We have shown that R will go to Q. That means that if P takes place, Q will take place as well. And if P implies Q, as we have right here, then A is said to be B. In other words, simply put, A is B if P implies Q. And we have shown that P implies Q because P implied R, which implied Q, therefore P implied Q. So remember, if you were able to show that P goes to R, then R goes to Q, Q goes to X, X goes to Y, Y goes to, say, C, then P implies C. Because remember, everything follows, If this one takes place, that one will take place, okay. If that one takes place, then that one will take place. That means that all of them will imply going down the line. If P occurs, R will occur. If R occurs, Q will occur. If Q occurs, X will occur. If X occurs, Y will occur. And if Y occurs, C will occur. So from the start, I can say P goes straight to C. In this case, P went straight to Q. And because P implies Q, then A is said to be B, or A is B, simply put. Therefore, A, oops, why is this red? Get it back to black. A is B. How do I know that? Because the definition said A is B if and only if P implied Q. And we have showed that P implied Q, therefore A is B. How do I know that A is B? Definition told me that. The definition said, if A is B, if P implies Q. We have showed that P implies Q, therefore A is B. So this is what you call a direct proof, because we can just go straight from what you want, what you started from, to what you want to get to. There's no nothing you have to eliminate or get rid of in order to get to what you want. We just wanted to show that A is B. All we have to show is that P implied Q. And we show that P implied Q from theorem 1 and 2. And because P implied Q, then A is B. Any question about that one? All right. Let me show you some more so you can get used to it, because that's like a warm-up. Mm-hmm.
Is it similar to like the transitive law thingy?
It's similar, yes, in a way, because the transitive, well, you're going to get to that soon, but transitive is a little different, because transitive says if A implies B and B implies C, then A implies C. So it's similar, but not exactly the same thing.
Okay.
Because that part of it about A going to C is similar to this. The only part is that you have to put justifications and sometimes do elimination instead. But this part of it right here is very similar to it. The direct proof. Sorry about that. All right, number 2. Oops. Here's the next one. This one is tricky. I want to remind of something. I should remind you from the start, you know. If I say it now, you're going to know when to use it. Well, I won't say it. Let me see if you guys remember it. If you had, well, Shanice want to see it because she didn't get the recording. Because if you didn't see last class, let me tell you, let me give you a hint. The class when we went around, we talked about inverse, converse, and contrapositive. We're going to be using one of these right now. Inverse, converse, contrapositive. If you forget what they are, I'll remind you. If I ask a question you can't figure it out, I'll remind you. But right now, we're going to be using one of these. Which one it is? Let's see if you can figure it out. All right. So we were given some things. We were given axiom 1. Well, there's only one axiom. What axiom 1 still? Which says S implies T. We were given theorem 1. Which says P implies Q. And we were given theorem 2. Which says that Q implies not T. Remember, if you missed it, this thing in front of the T means not T. So if T is saying something, not T means not the opposite. Not T means the T is not going to take place. For example, if T meant the thing is a triangle, not T means it's not a triangle. It doesn't mean it's a square or a circle. It means it's not a triangle. Could be any one of those. Just not a triangle. Could be a straight line. All right. We're going to prove. Put in red. Prove. What to prove now? If P, then S is impossible. So if P, then S is impossible. The next way to say that is not S. If P, then not S. In other words, P must imply not S. That's the layman way of writing that, or the shorter way of writing it. So if a question says if something, then the next thing cannot occur, it means not the something, or it is impossible, or just not the thing. All right. But the question didn't mention that, although you should know that. So let's draw up our little diagram again. We're going to have some justifications and some conclusions. I'm just going to shorten it now, get used to it, so I can just write like this. Conclusion, C-O-N-C, justification JUST. Might like a shortcut. Which I probably can load it to use as well. I'm not sure how many lines I'm going to need. A while ago, I did one too many. I think it's about 4 again. Let's find out. Let's put 4 for the start. All right. So, first things first. Let me see if you guys get it down. What we're going to start with?
We're going to start with P,
Correct. Why P?
because you say if P. You say if P, so we need to know if P is impossible to S. So we have to start from P.
All right. And what you're going to put for justification?
Q.
Mm-mm.
Oh, theorem 1.
Mm-mm.
No?
The G word.
Given.
Right. It's given. And it was given in our hypothesis right here. So starting from the P. Remember, whatever comes after if is assumed to be true. So it's given to you.
And
Right.
then the next line would be Q from theorem 1.
You all right? Sound good. Q from theorem 1. Because as you can see from from theorem 1, P goes to Q. What can we do next? Sorry.
Not T
Not T. Why not T?
from theorem 2. Because
Correct.
Q goes to not T.
Yeah, man, you're right, man. I just wanted the justification when I said why. And here's a tough one now. Can anybody figure out the last one? I'm going to give you a hint. It's a last step. So obviously is what you want. So that's telling you what to write right here. You see, it's a last thing. The last thing is supposed to be what you want. So what should be right here? Last thing. What is it that we want? I told you from over here.
Sir, I'm not sure because here say you have Q going to not T, but up here say you have S going to T.
But we know we're about over here yet. What did I tell you supposed to get over here?
Oh, not S.
Correct. Not S. Now here's the tricky part. How can we get not S from this? I showed you 3 words a while ago. I showed you converse, showed you converse positive, and I showed you both times that was the same thing. CON, contrapositive, and converse and inverse. Yes, I mentioned those 3. One of them is going to be used right here. Only if you can remember what they mean. But if you forgot what they mean, let me just remind you. If you have A imply B.
Contrapositive.
All right, contrapositive of what?
Of S.
You must have one of these.
The
Of what? What is the one we didn't use yet?
the axial.
All right, contrapositive of them one. All right, so before I'm not saying that is correct, but I want to make sure you know why. Let me just show you this thing. Can I extend this line? Yes, I can extend it. Good. Cool, that's all. Lovely. Now, here's why that's the answer. Why the contrapositive can work. You notice everything that we used given because it was given. We use theorem 1 that was given to us as well. We know it is true. We use theorem 2 for this one because that is true. All right, let's make sure I understand the flow of everything. P implies Q's that we have right here. Remember, no. If you put a letter below a next letter or some statement and you put next statement below it, it means that the one above implies one below or leads to it. So P implies Q is the same thing being said right here. P implies Q because you put Q right below P. So it means that if P took place, then Q will take place. Sorry. And we know that from theorem 1. Look at next one. Theorem 2. We see that Q implies not T. That's why we have the Q right above the not T. Because Q went straight to not T. How do we know that? Theorem 2. Then how can we tell that not T will go to not S? Well, here's how we know that is true. So this is what we said right here. But how do we know that this is true? Look at this now. Let's make sure you remember what we did last class, or whenever we did it. I don't know if it's last class or last week. If A implies B is a true statement, Matter of fact, I'm use a false one. I'm going to say true. True already. Then the contrapositive of that, which is the inverse and converse put together, will also be true, which is going to be not B, negated, and put not A afterwards. So the contrapositive of a statement is just the inverse and converse at the same time. It's negating both of them and turning it around. That's a contrapositive. And if the original statement is true, like we have right here, then the contrapositive will also be true. If the original statement is false, the contrapositive will also be false. That's how it works. Contrapositive will always be the same as the original in terms of its logical meaning or truthful meaning, if it's false or true. And I showed you some examples last class. I told you about I keep saying last class. I don't know if it was last class or last week, but I gave some examples where, for example, here's a good one. If there are clouds in the sky, then it is raining. That is not true. I want to make sure that this is stuck in your head because we're going to get some questions with this type of thing. So let me just clear one more thing and then go back to what we're doing. If there are clouds in the sky, then it is raining. That is not true. There can be clouds in the sky and there's no rain. Remember, this is saying if there are clouds in the sky, then it is raining. Remember, for a statement to be true, it must be true all the time. This is not always true. There can be clouds in the sky and there's no rain. If you turn it around, it is true. If you said, if it is raining, then there are clouds in the sky, that is a true statement. That one is always true. Matter of fact, let me come back to that later. So this we know is a false statement. This is false. What's the contrapositive of this? The contrapositive is to negate both of these things and flip them around. So the contrapositive would be
if it is raining, then there are clouds in the sky.
No. If it is not raining,
If
remember you
it's
must
not
negate it.
raining,
Right.
yeah. If it's not raining, then there's.
Right. If it is not raining, I would be writing this, probably should have said it. Then there are no clouds in the sky. So you negate both of them and turn it around. Are no clouds in the sky. So, make it shorter. Which is not true either. Right now it is not raining where I am, and there are clouds in the sky. So you see that both of them are false, and both of them are contrapositive of each other. So once you find a contrapositive of a statement, if it was true, it will stay true. The contrapositive was, if the statement was false, the contrapositive will also be false, like in this case right here. But if I give you a true statement, like if I had said, if it is raining, then there are clouds in the sky, that's true. The contrapositive would be, if there are no clouds in the sky, then it is not raining. That is also true. Make sure you think about them because they can trick you up, might sound like the same thing, but it's not the same thing. So the one that is true is, if it is raining, then there are clouds in the sky. That is true. You can't have rain without clouds. The rain comes from the clouds. And if you flip it around, negate it and turn it around, if there are no clouds in the sky, then it is not raining. That is also true. If there are no clouds, you can't have any rain. And if there is rain, then you have to have clouds. So both of those statements are true. So going back to up here, the reason why we knew that this was true, that we could use the contrapositive of axiom 1, is because we have accepted axiom 1 to be true. Therefore, the contrapositive of it must also be true, which is not T imply not S. That's how we know not T went to not S. So when you get some questions, make sure you can figure out the contrapositive of each one as well, because you might need it. So sometimes it might not be as straightforward as this. S to T, P to Q, Q to not T. Like we did a while ago. Everything was straightforward. I think a while ago we had the P went to R, the R went to Q, and then we get A is B. But in this case, you have to do some little tricky stuff with the contrapositive. P went to Q, yes. Q went to not T, yes. But we could not go straight from not T to S, to not S. We didn't get anything like that. We didn't get anything that says not T equal not S. But we did get this one, which is S imply T. And you can use anything. You can use the contrapositive of any statement that you get, any axiom or theorem that you get. Because the contrapositive will be true once the theorem was true or the axiom was true. Sorry. So that's why we could have used this, not T imply not S. All right. Any questions before the next one? That was number 2. Oh, number 2 disappear. All right. Let's go to number 3. Number 3. Write it down here. Oops. Let me carry it up. Draw the line first. All right. Number 3. What's number 3? No, I don't want to give you one like that yet. Not just yet. Let me give you this one. We're given these theorems. We're given theorem 1, which says Y implies not P. We're given theorem 2, which says R implies X. Theorem 3, which is S implies Y. And theorem 4, which is X implies Q. What a mix-up going on. Oh, I forgot to mention this part. I didn't even see it. Suppose we know... Oh, crap. I didn't want to do this one yet. I didn't realize it was this one, you know. Lord Jesus, Lord Jesus. Oh, well, whatever. You got 2 direct ones. Here's an indirect one. I didn't want to do indirect yet. Suppose P implies either R or S. And so you have these 4 things, these 4 theorems, and we know that P implies either R or S. So it's like an additional thing. It's a rule as well. We need to prove that R, beg your pardon, Q, my goodness, prove P implies Q. I don't know where I get R from. So we're given those 4 things along with this rule over here, and we want to prove this thing down here. So we know that theorem 1 says that, theorem 2 says that, theorem 3 and 4 say that, and P implies either R or S. We want to prove that P implies Q. Now, it's one of the tricky ones. So this one needs some thought now.
There are inverse.
Well, not the indirect.
Yeah, indirect.
It seems like that. I'm not even 100% sure. We can find out. Conclusion. Justification. Let's see how it goes first. So we have number 1 and 2 and 3 and 4 and 5 and 6 and whatever. Write up some lines. That should be enough for now. I don't know if it's going to be more than that. All right. So 1, where would I always start? When in doubt, P. Want to prove that P goes to Q, so start with the P. Why P? It was given. Sorry. Now, we need to get to Q. And if you look at this, if you go to R, you're going to go to X. I shouldn't be showing you all of them, you know. But let's say because of P goes to either R or S, let's pick the S first. If you look at this, you might see that the R goes to Q. So I'm going to pick the S first. S. Let's say, okay, S. I know I'm right properly because I thought you to do it. R or S. Why? Those are the logical possibilities. That's not how it's spelled. Oh yes, I see that. Logical possibilities. All logical possibilities. And 3, pick the S first. And if you look at it, you will see that try to get rid of the one that is not going to go to what you want first, if possible. So the S, first logical case, just like I showed you last time. Or you can write logical possibility, whatever. What can we get from S? I didn't write properly, right, bigger.
Why?
Why? How do you know why?
It's given. It's theorem 3.
Right, theorem 3. What do we get from Y?
Not P.
Not P. From what? Why? How do we know that?
Theorem 1.
Theorem 1. But not P is a what? What's the word for that? Start with C.
Contrapositive.
You're close. It's contra something.
Contradiction.
Right, it's a contradiction. Because we have already assumed that P is true, so we can't go to not P. It's like saying that person is a woman. Mm-hmm. That woman, no, sorry. That, person is a man. And then you say, yeah, man, that person is pregnant. That's a contradiction. That's not a man then. So it's like something that can't go so. So to go to S from P, sorry, will lead us to not P. So that means that we can't use S because it led us to contradicting what we knew to be true already. We know that P is true, but when P took place, we use S. When S took place, we get Y, but from Y we get not P. So it cancels S. Because we know that P is true already, but it carries us to not P, which is known already is to be true. It's like saying, okay, P took place, S takes place next, Y takes place, P didn't take place. But P took place already. So because P took place already, you can't say that P can't take place because it took place already. So it's a contradiction. So we have to use the other possibility then, which would have been R. And that's our next logical case. Can us write next or right second to what you want. Next logical case. Okay, I guess I needed more lines. Maybe 2 more.
What if I had put theorem 2 there?
What did we put what?
Theorem 2 for R.
Well, theorem 2 didn't come from, remember, it needs to come from P, you know. Right now we're saying P implies R. And theorem 2 didn't say that.
Oh.
So, right. So if you're going to use a theorem, it has to be going towards the thing that you're using it for. Okay, notice we use theorem 3 for Y because it went to Y. We use not P.
Okay, sir. I realize.
Okay. That's a good question to ask because I've seen people make that mistake before. So get better to ask it now. All right. What can come from R? Number 7. What comes from R?
X.
X, right.
Theorem 2.
That's theorem 2 now.
And then X to Q.
And then X to Q. How come?
Theorem 4.
And it's supposed to be in a yellow house.
So it's a kind of indirect because it eliminated something. And so you can say theorem 4 also rule of elimination. But we have shown that P goes to Q. So it's like an indirect direct proof because it went straight to it, but it eliminated something. Once there's elimination, it's indirect. But also once it goes directly, which we did right here, it's also direct. So that's why I didn't want to do this one yet. It has both of them in there. And I picked up one and didn't realize I picked up the same one that I didn't want to do. Oh well. But there's a different type of indirect now where you don't go to the thing at all. That's what I want to do now. Make sure you look at it before picking. If you have any questions, you can let me know. Oh, it's this one here. This is the one I wanted. You ready? Anybody writing? No? Any questions? No? Next one. All right. Up we go. Oops. That was number 3, number 4. Sorry. All right. We have, what is now? 2 axioms. So axiom 1. P implies what? Oh, not Y. How P imply P? I mean not P. Axiom 2. Not Q implies R. What else? Theorem 1. So 3 theorems. Theorem 1 is P implies not Z. Theorem 2 is what? Oh, here's the interesting stuff now. X implies either Q or Z. And last, the theorem 3, which is R implies either what? X or Y. All right. Now it is interesting. We want to prove that P implies Q. Again. Prove P implies Q. All right. Let's make sure I didn't make any mistake. P not Y, not Q R, P not Z, X either Q or Z, R either X or Y. Okay, good. All right, what time is it? 41. Okay, we have 40 minutes, almost. So we want to prove that P implies Q. And we have these 3 things. Well, 5 things. What did I get 3? Here we go. Draw up a little column again. Same business going on. Conclusions and justifications. I'll just write them as long as we go. First things first. What are we going to start with? Oh, by the way, look at it carefully. This one is a bit tricky. As a matter of fact, I'm going to do it the wrong way. But this one is the type that will cause the most trouble from everything we've done so far. Let me just make sure you understand what I'm saying. If you start with P, you're going to get not Y. Not Y. Well, you get 2 possibilities really, not Y or not Z. And you notice that if you do that, you're stuck right away. Because you can't go back from this one to R. Because, or not R. Because there are 2 possibilities here. And you can't go from which one is it? Not Y? Oh, did that already. Not Z, yeah. You can't go from that to X. Because it's 2 things. If it was straightforward like this, that if it had said X implies Z, you could use a contrapositive and say not Z implies not X. You can use that. But even then, if you do that, you get stuck anyway. Because X doesn't go to anything after that. But once there are 2 things like what we have over here, you can't go backward. You can't use the contrapositive. Because it's either this or that. You can't just pick one. So that means you have to have a different approach. This is the one that you have to pay the most attention to. This type. So here's what we're going to do again. We're going to do what we always do. If you don't get anything right, what you must always start with when you're unsure.
The table, the conditional.
All right. What? Wait, what's that again?
Condition of the table.
Well, you have a table, yes, but what are you going to put in what's the first thing you're going to put in the table?
The axiom 1.
Mm-hmm.
P, sir.
P.
The P, don't forget. I always start with what are given. The
Given.
hypothesis. Right, start with that.
P given.
That's an easy 2 marks. Don't miss it. You see, even if you don't know what to do, just put that in there. Take 2 marks and move on. Because at this level, in normal proof, sometimes you don't start from that. But at this level, in pulse geometry, the basic geometry stuff we're going to do, always start with a given. I keep having to say at this level because when you go to higher proofs, sometimes you start somewhere else. But you wouldn't have to learn that right now. Anyway, here's the trick now. As I said before, even though we started with the P, you see if it goes not Y, stuck. If you use theorem 1, not Z, stuck again. Because it can't go anywhere after that. Not Y, not Z, not carry us anywhere. It can't go backwards with the either or. So in that case, what we have to do, remember, there are 2 possibilities. P can either go to Q or it cannot go to Q. If you have a shape, the shape is either a triangle or it is not a triangle. Remember, the not means it can be.
So I think the next line would be not Q.
Oh my goodness, praise the Lord. You're the first student.
Axiom 2.
Oh no, you're going wrong now. You
Yeah,
were
but
right,
not,
but
so not Q, not the axiom 2.
it is there, but I didn't want it to say from Axiom 2 is actually
Oh,
indirect proof because you can't go to the thing directly, so you have to find a different way to go to it. And you were right by saying assume
not Q.
not Q. And I've been teaching this course for how much years now? I teach every year from start. About 16 years now. You were the first student ever said before I say it. That's Renee, right?
Yes, sir.
I might give you some bonus for that. I'll think about it for your test. Alright, and the reason is assumption for indirect proof.
Okay.
That's what you want to know. Assumption for indirect proof. And this is something you have to do because you can't go directly to the Q, so it has to be an indirect way. All right,
So the next line
next.
would be not Q to R from axiom 2, right?
Right. So you get R next. That's axiom 2.
Okay.
And you can notice now that things are going to fall into place because you can go from place to place now. What we can get from an R?
Either X or Y.
All right, so put X or Y. This one is going to be long. X or Y.
Theorem 3.
All right. Theorem 3. All right, let's pick. I'm going to pick first. Pick the Y first. Number 5. Y.
So we have to pick Y first.
But it's smoother that way. If you pick the X first,
You're going to have either Q or Z.
right, you don't have 2 either again. You just want to get rid of 2 of them one time. So it is what's the word they use? It is mathematically sound to pick the one that cancels first. Or cancels quickest. It's just like when you're doing integration. You use integration by parts. So I don't know if you guys do Cal2 yet. You would.
Yes, sir.
Oh, both. Okay, good. When you do integration by parts, you pick the one that differentiates the fastest as 0 first, as U.
Yeah.
Right, same thing. You get rid of the easy, quicker one first. So we would have chosen Y, and Y leads to what? Sorry, no. First case. That's what him, so let's pick first case. I don't know. Y leads to what? This is a trick one, no. You see who get this first.
Y leads to not P.
Wait, Rennie, you like this thing, man? How you know that?
Sir, me just because you have not Y up here, so and then down here so you have Y. So if it's Y, then I opposite. So I don't know
All
how
right,
to
what's the
explain it.
justification?
Me just know.
You can explain, but start with C.
Oh, contra Something.
Contra something. Well, okay, I'm going to go say contra something.
Contradiction.
No, sir. Well, is that contradiction? Yes. But that fancy word, man. Shanice said, "What about the word?"
Contrapositive.
Right, contrapositive.
Okay.
It's a contrapositive of what?
Not why.
It's one of these.
Oh,
Axiom one.
All right. It's a good thing I'm Shanice said, man. All right.
mhm.
All right. So both of you working well together. Because remember, axiom one is, make sure you understand that one properly. Axiom one is saying P implies not Y. That's all. I think so. Yeah.
Yes.
So if you have A, not A imply not B, contrapositive is negate both of them. Negation of A is A, negation of B is B. And then you flip it around.
Going to A, yeah.
So if you negate the Y, put it at the front, negate not Y, sorry, and negate the P, you get that. So Y goes to not P. So the contrapositive axiom one is actually flipping around the P and the Y and negating both of them.
Like an inverse.
Right, it's an inverse and a converse at the same time. So converse is reversing them, and the inverse is negating them. That is correct. So you negate them and flip. Anyway, so that's a contradiction. So Y is out. It's a matter of fact. Yeah, Y is out because Y led to a contradiction. So we can go to X, which is the other case. X, second case, or next case, right? Next case. Drop a line. What can we get from X?
Q or Z.
All right. Q or Z. How come?
Theorem 2.
Theorem
Yeah.
two.
Oh, sorry. Yeah, in case you guys can't see. Theorem 2. All right. Which one are you going to pick first?
Z.
Yeah, man, because Q1. So put the Z first. I
Oh,
know there's nothing that goes to Q anyway. You see? Look up there. Nothing went to
yes,
Q.
sir.
All right. So Z. So Z goes to what now?
Z goes to not P.
All right. And why is that?
The contrapositive of theorem 1.
Correct. If you flip this thing around and negate it, you get Z goes to not P. So contrapositive of theorem 1. Not P. Contra. I hate writing this word takes so long. Contrapositive of theorem 1. All right, that's a contradiction as well. I need to put little 2 arrows for the contradiction. So look at what has happened so far. We have shown, and by the way, you can't go put Q because we already assumed not Q. So not Q can't lead to Q. But we have shown that everything from not Q, you notice even though this one said Q or Z, we can't go put Q. Well, you can put Q, but not for the reason of saying second case. Oh, geez. Wait, I moved a little fast. I didn't put the choose Z
Yeah, should
first.
have. Yes.
Yeah, we'll fix that. Sorry, I didn't realize I didn't pick it. Then I can move it like this. Please work. Ah, it worked. Good. All right, so let me just increase this line a little bit. Drop a next line right here. And put in the missing thing, which was supposed to be Z. First case from the second thing here.
First. Yeah, first again, sir.
But a different
Okay.
different Q or Z. I could put only case because you can't pick not Q. You can't put Q because we already assumed not Q. So you couldn't have actually put Q. No, we can't put Q like how we get the contradiction here because no, based on what we have seen, everything that could work. Look, we use everything up there now. Well, let's make sure I show all them to you. We have used Z,
Yes,
we
sir.
have used X, we have used Y, and we have used R. So Z, X, Y, R. And those are all the possibilities. See them here? X and Y, Z, and R. Nothing else was there. There was only P, R, Q. So because from P to not Q, remember, it's like saying it's either this or that. It's either a number, it's not a number, real number, not a real number, triangle, not a triangle, circle, not a circle, something like that. So we have said, okay, there are two possibilities. It's either going to be the Q or not the Q. When you choose not Q, contradiction. Contradiction. All the possibilities led to a contradiction. So our final conclusion is therefore Q. Do you remember what the justification is? Start with the R. 3 words. You're going to always use that when you use indirect proof. Let me start off the first word. Rule.
Rule of elimination.
There you go. Shanice couldn't answer that one because she wasn't here for that, so can't beat her. I'm going to beat Harold though. All right, so that's it. So that's how indirect proof goes. You eliminate all the possibilities and leave, okay. Oh, by the way, they should always go to a contradiction. If they don't go to a contradiction, it's not indirect. Either it's not indirect or you made a mistake. One of the two. So once using indirect proof, you can always eliminate stuff by contradictions, and then whatever is left is your your eliminated final eliminated result. That's all that's left. Let's see if I reach 20 minutes left. And I want to stop so quick, but I'm still 13 minutes. Let me see if I can find one more. All right, we have one more thing. Let's do it. That's 1, 2, 3, 4. 4 examples, 5 examples. Well, that's good enough, man. No, you know more than that. So one more, and we're finished. Oops, what happened? All right, 5th example. Any questions, by the way, before I go to the last one? All right.
No, sir.
No.
Okay. Oops. All right. Finalmente, number 5. All right. What we're given now? Oh, what do you stuff? Oh my. Definition. So next class you can start geometry. Now that you know how to prove the stuff, we can go to the first part of geometry, which is going to be our incidence axioms. A is said to be B if and only if R implies S. So it's not the same one that I said before. Different one is. We have axiom 1, which is what? R implies Q. Axiom 2, oh sorry, theorem 1. No more axioms. Which is what oh, what is this? If A is C, if A is C, then what? Q implies T. Okay, interesting. So if A is C, then Q implies T. All right. Theorem 2. T implies S. All right. We want to prove if A is C, then A is B. What? Okay, interesting. If A is C, then A is B. All right. That's weird. Give me a minute, please.
But theorem one said if A is C, then Q is T. Jesus, peace.
Sorry, what you said now? I was hearing your voice.
No, may I say, and theorem one says if A is C, then Q is T. This look like headache now.
Let's hope it's not so bad. As a matter of fact, based on what they say here, it should take 6 steps. Let's find
Okay.
out.
Yeah, for the one, everything's straightforward. If you got
That's easy.
something, no.
All right, nice. Let's see if we can pick up the straightforwardness. So we have justification and conclusion again. That's right. Con and just. What is it, Miss Shanice? Or anybody? First thing is what?
A.
A. Yeah, all right. You're missing something.
A is C.
All right. A is C. Remember, always start with
Given.
the if portion. Whatever they're giving the if, that is your hypothesis. That's what you're starting with. You assume it to be true. So we
And that's
assume A is C.
given.
All right, it's given. All right.
Given, sir.
Next.
So if A is C, then Q is T for the next line in theorem one.
Um,
What's up?
oh,
What's up? Yeah. Q is T, theorem one.
Q is T, you say. All right, hold on. Before I write it, where are you going after that?
We're going to go after which one?
After Q is T.
After Q is T, we're going to either use Q or T. But I use T, sir, and then T will go to S.
All right, write it down. You're close, but you're missing something. Hold on. Let me help you out here.
Oh, the
Remember,
first
we want to
case
go.
or something like
Hmm?
that, right? First case. When we put
No,
the T,
not necessarily. Because think about what you want. How do we know that Q can be T? Confuse me.
Hearing to
A, C.
see, it's
A is not C.
All right. If A is C, then Q is T, correct? Are we going to use R at all?
Uh, hold on, sir. So just write the line in 1 1 and then we reach to the party.
Yeah, but we have to get to Q first. You can't just drop on the Q. Well, the only way that Q can be T is if Q
can
take place.
You will use the
Alright,
addition in order to
so,
get the Q.
yeah.
Yes, you need
so
the
if
R to
we
get the
don't
Q.
use the T, sir, then we can use Q and then Q will be not R.
No, you got too far now. You think too hard, man. All right, let me help you out. You see, when you're doing these proofs here, each thing that you want to use, you have to make sure you get something to bring it in. The only way we can bring in the Q is if R took place to go to the Q. Even though if AC then Q is T, fine. But how do we know that Q took place? We have to have the R first. That's what I'm trying to get across. It's like saying, yeah, I get it. Okay, good. Because Q cannot go to T unless Q took place, and we didn't establish that Q took place yet. We're starting from AC. If AC, Q is T,
Oh,
yes, but when did Q take place? So this is a little funny one where you have to say R or assume R, put the assume in front of it. Because the only way the Q can come in is if R took place. So assume R, which is assumption for R imply S.
That would
I
have come
think
from the definition.
but sir, you couldn't like
right.
use the definition and put A, like use A from the given part and then say A is said to be B over the next side if R go to S.
You can, but the thing is, where would R come from? We have to put it in there somehow. That's the problem. Sorry. Is R a matter of fact? R is going to be the one that's doing everything right now. You know, R is going to go to Q and then go to S. I cannot give it that way, but the R is actually going to be the one doing the work. The only way you can go to S is if R is in there somewhere, and R can only go to S if it went to Q and then go to the T and then go to the S. You will see. So that's why when you're doing these proofs, look for the flow first. Because remember, you need to go from something to something to something to something to something. You were correct about saying the Q imply T, yes. But you can't get to the Q imply T and the R imply S and whatever without starting with the R. You know, if you look carefully, everything goes from R.
Oh, if we did use Q to T, we'd have stuck at the S.
Right. There you go. There you go. And you wouldn't have proven that the R goes to the
And
S.
F then go to the R.
Right. Lovely. All right. So number 3 now. You can go with your stuff you were saying. What comes from R?
Q.
Q. How come?
Axiom 1.
Yeah. So this is one of the tough direct ones. So Shanice was correct that it's direct. But it's a little tricky because you have to put R in there. What comes from Q?
T.
How you know that?
Well,
Then
theorem
if
Theorem
A
1.
1.
is yeah, theorem
All
1.
right. Because theorem 1 can be used because A is C.
Mm-hmm.
Establish at the start.
And then T leads to S,
Lovely.
and
Change
then
to S. Where T lead to S from?
Theorem 2.
O.
Mm-hmm. Let me hear the niceness now.
Therefore.
As Risha said.
Reach a nice step now, man.
Therefore, sir.
Eh?
No. We can therefore that
Yeah, man, you can
we have
therefore. Therefore.
there.
Matter of fact, most of the answers, if you look in the textbook or other people's book, you will see they have therefore. I just lazy anybody write it. Like have the therefore Q and therefore I could have put therefore for all of them. But anyway, why did you write it? Okay. Therefore what?
All right, let me say this properly. We don't want the foolishness.
So,
It's basically
sir,
proven, but how
R,
does that?
What you want to prove?
that R go to S, R do go to S.
Mm-hmm. Just show that already. See there? R go
That
to S.
A is B.
A is B. Correct. Therefore A is B. How we know that?
From the definition.
There you go.
Definition.
Definition. Because we said A is B. A matter of fact, definition says A is B if and only if R implies this. And we've shown that R implies this.
Definition is like a condition.
Yes, it is. It is definitely a condition. Because the only way we can get that thing is if that condition is met. That is it. All examples. I show you 5 examples. I don't even know if I have any more to show you. I show you everything that the book had in for the questions. They had 5 exercises. That's all of them. Anything after this, I have to make it up for a test. Well, we have 30 minutes anyway. Let me see if I can find any fancy thing. Oh, G's and P's. Yes, I should have asked about this. So, any confusion about that? Everything good?
Oh, so it's fine.
All right. No, I'm going to show you. Remember last class I told you about the if and the then, the hypothesis and the what do you call it? Conclusion.
Yes.
Remember, whatever comes after the if. So if P, then Q. The Q is what you call the conclusion of your statement, and the P is your hypothesis. Now, some statements you don't see the word hypothesis. You won't see the word if, and sometimes you don't see the word then. So sometimes both of them are missing. I'm going to give you some statements now, and you will see if you can tell me. All right, remember the if part is the one that you're assuming to be true, and the then is what is going to lead to. So I'm going to give you 3 statements, and you tell me which part is the hypothesis, which part is the conclusion. Here's the first one. First statement is 2 angles. Maybe I should just read it. I'm going to take a while to write it. Here's what it says. 2 angles whose measures are each 30 degrees are congruent. Let me say that again. 2 angles whose measures are each 30 degrees are congruent. What's the hypothesis? What is the conclusion? Two angles whose measures are each 30 degrees
That
are
part is the hypothesis, sir.
which part?
The part from 2 angles down to 30 degrees, you said,
Yeah.
is the hypothesis.
All right, correct. So the part that says two angles whose measures are 30 degrees are each 30 degrees, that part is the hypothesis, and the congruent is the
Congregant is
conclusion.
the conclusion.
Right. I want a little longer, so I'm going to write it. I'm going to write this one. This one is shorter. Concurrent lines. What? Hold on. Say this wrong. Oh, the medians of a triangle are concurrent lines. The medians of a triangle are concurrent lines. That one is
The
nice.
median of
We have to
triangles.
try and the congruent lines. Congruent lines are the conclusion.
Fine. I don't know, Brighton. Okay. Concurrent lines. The conclusion. What's the hypothesis then?
The median.
The hypothesis is what you said the first part was?
The median of the
Medians of a triangle.
The median of a triangle.
median of the whatever.
Medians. Right. Last one. Success can only be. Sorry, beg your pardon. Success can be achieved only by hard work. Success can be achieved.
Success can be achieved is the
Well, I'm writing down because the one I give you the trouble is no
is the
success.
conclusion.
Success have to be the conclusion.
Success can
And
be
achieve.
achievement is the conclusion.
What I want to say. Well, I'm writing down because success can be achieved only by hard work.
Oh, okay. All right.
And only by hard work would be the hypothesis.
Hypothesis would be hard work and success have to be the conclusion. Because without success, well, the
Without
success
hard
and
work,
other
success.
you can have success.
Okay. I'll have a look at sense. I'm gonna get everything right. Okay, because
You have
this
little
the hard
sense,
work
sir.
leads to the
Yeah.
success.
Yeah.
Okay, lovely. We get all of them right. So
But
if the
not
question
all
doesn't
the time.
mention it,
Not all the
sorry,
time.
go ahead.
It's not all the time. Hard work comes from success. It can be other ways.
Yeah, man,
Then
that's
it
true,
would, then it would be rule of elimination.
Well, no, he was just talking
We're
about
looking
what
at
they
the
actually,
context in which
the
it
actual
is used
message. Yeah.
right now. This
Yeah,
context.
so he wasn't saying that it's not the hypothesis. He wasn't saying that it's not always true for this what they're saying right here.
That's
The Chinese
true.
proverb. Yeah, but he's like, yeah, man. Some people get success from all kind of foolishness, not even hard work. Matter of fact, you have some children that's born into success. So, what I suppose if you want to be successful in what you're doing, that's to be hard work. But anyway, so yes, hard work is the hypothesis. Success being achieved is the conclusion. Okay, lovely. What else I wanted to mention? Yeah, so next class we can start with, if you want to read ahead, this topic here. There are 5 of them. The incidence axioms. So these are things that have been accepted as truth, prophecy, gospel, but they were never proven. So geometry is based upon these 5 axioms, which we will look at next class. So we're going to start the history of geometry next class. So this was just the basis, the foundation for doing the proofs that we're going to be using. But we're going to start with those for geometry. So any questions before we leave?
Sir, do you have a course outline?
Lord Jesus, I keep forgetting to
The
post it.
textbook.
Look here.
Is there
You guys,
Sir, we don't need a textbook because it's hard to find the textbook.
yeah, it's hard to find. You don't need it. I mean, you
the
can get it if you
textbook?
want.
Send
You
it
don't
to
need
me and I'll see if I can source it online.
it.
The
It's
PDF
called
version.
Geometry. All right, tell you what. I'm going to post an outline with it. It's called Geometry: A Discovery Approach by David C.K. So, college geometry. What color is it? Brownish and yellowish. Brown and yellow.
Yeah, just
College geometry. A discovery approach. So that's part of my writing class. A discovery approach. David C.K., that's the author. David CK. All right, so I'll post outline in case you want to get more information about textbook as well. But we're gonna start here next class. This topic here.
Okay, sir. So, sir, just to prepare to be successful in this course, we don't need a textbook, right? Because you'll give us everything we need, as you said, and the course outline will guide us, right?
Yeah, man. Yeah, man.
Reason I'm
I know.
asking is because I spent 5 hours this morning trying to go through a textbook for another thing, and it coming like it's a waste of time.
Is it calculus?
Yeah, yes, sir.
Yeah, man. Now, I wouldn't advise you try to learn from the textbook. It's dead.
Well, I waste 5 hours already, and look like I get sick because so
Here's
I
my advice for calculus for that textbook. When I teach you, you check the questions. Don't try to learn it on your own from the textbook. That textbook is built for people like me who know calculus already. The way they structure the thing is not for first learners. I can tell you that.
okay, sir. Cause Spanish easier than it.
There you go, man. You're off, man. You're off. So it's not calculus is hard, and the textbook makes it look hard.
Yes, sir. It's true.
All right. So I've never advised you to use a textbook to try to learn. Just for practice. All right. But I mean, it's good that you're trying, though. But don't mash up your head. Not with that textbook.
I'm already sick, sir.
Okay. All right, people.
All right,
So
sir, I think I found the book. David
soft copy.
CK, right? The soft copy. It's about what 600 and something pages.
Hold on.
You can keep it. I don't want it.
641. Sir, so if you want me to send you a CK, David, right? So I found the book.
They found it. Okay, nice. They can send me so I can confirm the right one, but I think it's about 600 or something pages. Yes. At the back it doesn't
Yeah.
tell me the page number, so I'm not sure. But
All
I think
right.
that's about that.
Let me just send it. All right, I can send it to your email now.
Okay, cool.
And you can
Okay.
let me know if that's the book.
All right, no problem. I'll do that.
If you check your email.
Yeah, man, I'll check it right now.
All right.
All right, so well, I suppose all of you. No, wait, not Rennie.
All right.
I'll see you tomorrow.
Come in.
Rennie, you
Yes.
doing that, bro? Actually gone. Okay. All right, so
All
see you
right,
guys
sir,
tomorrow.
just wait. Sir, just wait. Let me see if it's it.